You replace all hydrogens with metal, it's called tertiary. That's the most stable form of carbo. If you replace two of hydrogens with metal, it becomes more stable than none, right? But it's not as stable as. So, with if you have a carbon that has a charge on it, and only one substituent, it's called a primary carboton, because that carbon with the positive charge that's only attached to one other. If the carbon is attached to two other carbons, it's called a secondary, and three is called a tertiary. So here's the rule. For carbocation stability, and this is always true, primary carbotons are less stable than secondary, and secondary are less stable than
tertiary.
And tertiary are less stable than. You can't have one because you can't have. What's tertiary less stable than? We already have a positive charge. We have a positive charge. What could be more stable than tertiary? We already have a positive charge, not neutral. We have a positive charge. What could be more stable than tertiary? Resonance. Resonance trumps everything. I know you guys forgot. I want to tell you, you're going to remember resonance for this chapter, for the next chapter. In chapter 25, where we have 4/2, you're going to say something. You better remember resonance. Right? That's why we spend time on resonance. You can just enjoy giving those questions for the exam. When you have a charge, the best way to stabilize the charge. Yes, if we have to have a charge, the best way to stabilize the charge is. So, primary is less stable than secondary, secondary is less stable than tertiary, and tertiary is less stable than resonance. And the way it stabilizes by hyperconjugation. So, increasing stability, primary less stable than, secondary less stable than, tertiary. So, if we can have that, and we have a secondary one. We have a secondary carboton. A secondary carboton is what's more stable than secondary? So the molecule looks around and say, can I get a range to go from secondary to tertiary? If the answer is yes, the molecule will. And that's the tricky part. How does it share range? It shifts the curved electrons with whatever attached to it. What's attached to them is not. And the way it shifts by when it rearranges, it tries to move the smallest thing first. So what's the smallest thing usually? Smallest atom. But if you don't have a hydrogen, in organic chemistry, the smallest thing after hydrogen is metal. CH. What's after metal? What's next in order of bigger than metal? Atom. What's bigger than atom? What's bigger than proton? Okay, so the point I want to make is when we rearrange the smallest to what if the smallest is a decade, which is 10? Can you rearrange that? If it's the smallest, the answer is
yes.
Anything can, but we start from the
smallest.
We always have the idea for rearrangement is you must get something more stable. If you don't get something more stable, it doesn't happen, right? Water, if I put a bucket of water on top and I pour it, it will drip all the way down here, right? Because energy, right? If I drop a bucket of water here, it's not going up to the top, right? And so the action will always go in the direction where we get more stability because the energy favors that. So let's look at a couple of examples. Here's a carbocation. You see this? What kind of carbocation is this? Let's see. How many carbons does this carbon have attached to it? One. If you have a carbon attached to two carbons and it has a positive charge, that's a secondary carbocation, right? Secondary carbocation. Now, if you shift this hydrogen, see this hydrogen? If you shift it, take the hydrogen and the electrons, move it to the other side. Now the positive charge is here, and the hydrogen is on the side. Let's look at this carbocation. How many carbons does this new carbocation have? 1, 2, 3. That makes it a secondary carbon to a tertiary. We make a molecule more stable. Does that happen? All the time. This actually happens all the time. Because we went from something less stable to something more. Now let's look at the bottom. This is the same thing, by the way. This is the secondary carbon. On this carbon, what's the smallest thing you can move? What do we have attached to that carbon?
Methyl.
Methyl, or methyl. Do we have a hydrogen? If we did have a hydrogen, will we shift in the
Hydrogen.
Well, we don't have a hydrogen, so the smallest thing here that we can move is a methyl. Can we move a methyl? Yeah. Same thing we move the hydrogen, pair of electrons, just move to where the positive charge is. There's your methyl now. And now we went from secondary carbon to a tertiary carbon. You can only have a shift from the carbon that is adjacent to the positive charge. You can't have a shift from like 7 carbons away. It has to be positive charge, a carbon right next to it, and it must form something more stable. I'll give you an example. What if, I'm going to go back to this, I want to show you, because I've seen those from exam days. What if I decide, see this hydrogen? What if, is that a hydrogen? Yeah, I just proved, right? Can I shift that hydrogen? I'm going to shift it. I'm going to shift it. I want to show you what you end up with. You end up with this. We started with a secondary carbon. What did I end up with? I went from something more stable to something that's like saying water is going up the stairs by itself. Right? We know that's stupid, right? I mean, I want you to know, I use the word stupid, not likely, because you're telling me you're making something that's stable or something. Please don't do that. Like, always the idea is that you gotta make something that is more stable. So the idea of the shift and the arrangement, when you have a carbocation, anything on adjacent carbon can shift. Hydrogen called hydride, methyl called methyl, ethyl, propyl, cyclohexyl, whatever it is you want to shift it, can shift, but you can only shift things if you get something that is more. By the way, more about this is showing you what's going to come later on. So, but I want you to be able to name it. Electrons picking up a hydrogen, this is called a proton, right? Water leaving, this is called loss of a leaving, right? Yeah. This is the arrangement, right? And finally, we have a nucleophilic attack. This is like a complete mechanism that we'll talk about later, but it has all the different. Or sometimes you could have 2 in 1. Like here, a nucleophile is attacking this carbon. That's a nucleophilic attack. And chlorine is leaving. So it's a nucleophilic attack and loss of the leaving group happening in one. That's right. So it's just, again, what I'm trying to say is that all the mechanisms from chapter 17 to chapter 27 or 28, all of them must have those 4 steps. So if you understand those 4 steps, it's going to work out for us. Right, so things that you shouldn't do. See how the electrons, see arrow, so the pair of electrons attacking the carbon because the carbon has a positive charge. And notice the arrow starts in the middle of the bond. Why in the middle of the bond? Because the middle bond is made up of a pair of, an arrow always starts at a pair of electrons. This arrow is unacceptable because this arrow is starting at the top. It has all arrows always start at a pair. When I say a pair, I mean a pair. I mean a pair. I mean a pair. Or a single bond, right? It's not like this. The arrow must start in the middle of a pair of electrons, whether it's a bond or a. So what's wrong with this? We just draw this arrow. I want to show you, I'm going to draw the product. If we draw this arrow, right, we get this metal, hydrogen, hydrogen, chlorine. This carbon now has carbon can never have. So please be aware of that thing. So if that happens, that means you're missing a step, and in this case, the chlorine is. So again, let's name them. What are the 2 steps happening? You can fill that because the option is attacking the
Thank you.
carbon. That's number one. Number two, loss of the leading group, that is the chlorine. So again, when you draw arrows, make sure that your arrows always start electrons. Why is this unacceptable? Because here we have two hydrogens. That carbon has no positive charge, right? Carbon between carbon and hydrogens, you can't attack it because it has to be an electrophile. Yes, young lady, I don't know what you think.
So it's still go with the mass positive because I know it couldn't go more than like this. Because it's like it's so far away.
What's far away?
Like so for example, if it happens to carbon,
Yeah.
would the resonance still be able to go there? Because I thought it was
It's not the resonance. I want to show you. So actually, this is I mean, you're like reclassed, but it's fine that you asked. Because I want to show you this. So say we have this is going to come in chapter 8, which is fine. Say we have say this is chlorine with leading group, right? Now, the question is asking is, can the double bond attack all the way here? Right? Very good question. The answer is not if you look at it this way. Now, this is all single bond, right? Can this molecule rotate? Yeah. At some point, guess what? It could be in. It's not the most stable conformation, but the molecule, when I say most stable, that means the molecule spends most of its time in but it's rotating all around. So at some point, for a fraction of time, guess what? The pi bond and this are right next to each other. So guess what? This will attack and this will. So again, I appreciate the question. It's a little ahead of time, but yes, don't think that the molecule is always going to be linear. That's why when I talked about those in chapter 4, when we do the confirmation, I said there is the most stable and the stable, but if you have single bonds, the molecule can do whatever you want. And at some point, you're open-minded, it could be exactly in this angle, and I don't have to convince you that, you know what, it could do that, right? It can't jump several atoms then, do it. So we'll get to these later on, but, you know. So, what kind of carbocation is this? Second. It has two carbons attached, right? So this is the carbocation, it has 1, 2 carbons. So it's secondary. Secondary is, by the way, anytime you have a secondary carbocation, right away it's not stable. And if we can make a stable ruler, let's look at the adjacent carbons. We have no hydrogens here. Can I shift over both sides? And why? Yes, no, maybe. Can we shift the hydrogen? Yes? No? No. Why not? If we shift the hydrogen, we end up with this carbon, right? What kind of carbon is this? It's still secondary. Is it more stable? So what would it have? Guess what? This does not. Is there a hydrogen here? Yeah. And we shift that hydrogen. Why? Because if we shift this hydrogen, we end up with this carbon, which is that is the hydrogen. So when you have first, okay, two things I want you to think about. One, you have a secondary carbocation, it's not stable. It will definitely rearrange, right? The question is, what rearranges? Well, look at all your choices. You have a carbocation, look to the right and the left, where are hydrogens, right? And shift them in your mind. If your carbocation that form is not stable, that shift is not going to be And so if we shift one of those hydrogens, we go from secondary to secondary. Why would that happen? It wouldn't. Whereas if we go shift this hydrogen goes from secondary to tertiary, that means we form a more stable carbon atomic, and therefore that shift will actually happen. About the way I have show you, I have. So if we shift this hydrogen, we go from secondary to tertiary, which is more stable. If we shift the other hydrogen, we go from secondary to secondary, which doesn't make it more. So stability. One more time. Primary is less stable than, and secondary is less stable than. And what's the most stable one? Resonance. So, what kind of star, what kind of that? That's a tertiary. How do you know? It's a carbon atom that has a carbon that's attached to three carbons. Would we have a shift of tertiary? Only if we can show. And look, if you shift the hydrogen, look where the positive charge is now. We went from tertiary to tertiary, but tertiary to tertiary. Professor, you said that, well, it's true. However, this tertiary now is stabilized by that one. So tertiary is stable, but more stable are resonance structures. And if you can see that, so we went from tertiary to tertiary, which really can argue that. By the way, if there is no resonance, that would not happen. However, this tertiary is stabilized by resonance, which makes it more. So I'll tell you why this is important. Let's look at this model. If you have to have a nucleophilic attack, where would the nucleophile? These two. Why? Because that's the most stable form of carbocation, because that's how the molecule spends its time. And so it's not going to be attacking this carbon because this carbon is short-lived and it forms resonance which lasts a little longer, and that's where the nucleophilic attack will take place. So nucleophile attacks the most stable form of the carbocation. What do we call this step? Proton transfer, because it's attacking a. What do we call this step? It's a nucleophilic attack. It's a purple electron attacking a carbon. What do we call the bromine leaving? Also leaving. More about these. What do we call this? Is there a proton transfer? No, it's a nucleophilic attack. What about this? The opposite of nucleophilic attack is a loss of leaving. More about reversal hydrogen. What really matters is you knowing that rearrangement is not reversible. Why? By the way, a lot of reactions, and you guys know that in equilibrium are reversible. Why is your arrangement not reversible? Because if we start with a secondary carbon, when the reaction rearranges, it becomes a tertiary. Why would it go back to being a secondary? It's not going to happen. So those reactions are not at equilibrium and they do not go back. We are done with this chapter. By the way, none of this, I don't have any questions on the exam to solve, because I don't get questions saying what are the steps. You know, when I show you the mechanism, I'll show you the mechanism, talk about all the different steps. I did say an hour. Wow. By the way, I'm not that organized, but I always have mental, like I come in and I have mental image, I'm like, I'm going to do chapter 6 by Paul, and it's like, shit. It just happens. It's like coincidence. All right, so the next chapter is